Good morning and thank you for joining us. My name is Tyler from Mount. I'm co-president of the RDAO, and we're here to present with Erica Holtz from Power Air and my colleagues from Ellison, plus Paul from Transport Canada. We're here to present our experience on electric energy systems, certification of electric energy systems today. See the context? So yeah, I already mentioned. It's not. No, I brought my phone. Oh. So as I mentioned, Erica and François sitting here with us. Paul, are you coming Institute?
I'm here in person.
There's Paul. Thank you. So the context of the presentation is Ellison is involved with the electric aircraft conversion of the Piper Archer for CAE. We have some our honorary delegate for performance there, specialist in performance from CAE, Richard Alexander is also with us. And so we've been working with CAE for the electric aircraft conversion of the Piper Archer, which involves the new battery system installation, like remove the old complete power plant and energy system, the fuel system, and putting in new electric propulsion and battery system. So today, that's our project. Eric is going to be talking about her experience with the electric lever conversion. Some of the elements of the conversions are common, and so you will go deeper into these aspects of the technology and the certification challenges. So we'll turn it over to Erica. Is it? Yeah. Okay. Yeah, I'll turn you over to François.
Thank you, Ty. From here. So, good morning, everyone. I'll take you into our journey into the world of ESS, Energy Storage System for propulsion aircraft, propulsion aircraft. Bear with me. We're gonna start from far, and we'll transition to today's situation. So we're gonna start with the introduction of electrification on the transportation a while ago, and why is that? That's because it was great improvement in the energy density. We were living from 50 watt hour to 256 watt hour, so a 5-time capacity, which led to now it makes sense to have such energy source for propulsion a couple of years ago. Just for your information, gas is about 8,000, so we're not there yet, but we're coming and we're improving. But gas engines are not as efficient as a fuel engine, so there's a lot of mathematics that needs to be there. So it's not exactly 8,000, but it's close by 8,000. So we're going with lithium. There's some, of course, some inconvenience with lithium that we know it's hard to predict what's the remaining energy. There's a lot of impact with the aging, how much you use, how much you currently use. Temperatures and a lot more. Of course, it's limited cycles that someday you'll have to change your value, which is an exhaustive exercise and a costly exercise. Some challenge with the storage as well. And the other one, and that's the one we're going to discuss this morning. It's the thermal runaway hazard. What's a thermal runaway? It's an uncontrolled self-contained chain of reaction leading to rapid increase in temperature. So it's not an explosion, but almost, and it goes very, very, very fast. And there's multiple causes that can bring us to a thermal runaway event. It could be overcharging, overheating, some defect, some external agent that can lead to that. They're hard to predict, and they're kind of spectacular when they do happen. We saw a lot of them in the news with the cars. We saw a lot of them in the news as well with the phones and laptops a couple of years ago. So it's well publicized, those events in the world. So what about aviation? Now it's in the car, it's well known, it's well accepted in the cars. Aviation, we're not there yet, obviously, we all know that. Lithium, although it's been introduced offshoot, let's say, in the aviation with the Dreamliner in 2011, when Boeing actually set those lithium battery for their APU starting battery as part of their type cert. Of course, that at the time was new and novel. A new framework was used for that. Some special conditions. They also used the fairly new DO311, which is the MOPS for the chargeable batteries. So, kind of setting the pace to installation of those type of batteries. Now, almost a year, 14 months after delivery of the first aircraft, there was two well-known incidents, the Logan one and the Al Japan aircraft one. So thermal runaways on the batteries. Luckily, there was no one injured. That one happened on the ground. That one happened right after takeoff, and they were able to land and evacuate safely the aircraft. But that put a cold shower on that whole idea of having lithium on board of the aircraft. So those aircraft, you must know that the 787 was grounded for 3 months, and it was like in deep investigation to what happened to that. The NTSB finding is that the design was not adequate and certification, so they did not anticipate such cascading effect in the thermal runaway. So one cell goes into thermal runaway, and the next one, and the next one, and the next one. That's what's happened, and was not well defined. So what's the legacy from that? After the 3 months and after a couple of going back to the drawing boards, NAC was published in 2015. Which set the basis of the installation of the lithium battery. This one formally recognized the O311 as your basic for the compliance of the installation of the lithium batteries. And it's layouts here some objectives to ensure your safety on installing and testing those batteries. We saw a couple of years right after this AC, there was an evolution to the O311. They realized that although Boeing followed the O311, they realized that actually was not strengthened enough, was not taking into account this containment of thermal runaway. So they went to the O11, the 311A in 2017. As this was a pivotal point for lithium-ion in 2013, well, we're now seeing evolution on that industry. So now we're seeing a lot of smaller craft that want to use this technology to do propulsion. And so we're at a new keystone now, a new milestone for lithium-ion that were used for ship batteries. Now it's going to be used for propulsion battery. If we and what's been laid out there in the past, in the 2013, well, it's obviously not adequate for propulsion batteries. For instance, if we just look at the DO311A, with the latest version, it's looking at the energy category, and the largest one here is 200 watts. Not kilowatt, but watts hour. And for comparison, if we look at your graph, your e-beaver, I believe it's about 160 kilowatt hour. So it's not even in the same ballpark. So it's not. It needs to be adjusted for that. If we look at the DO311A, see what it is right now. That document gives you some safety requirements for the thermal runaway containment, and it's giving you some descriptions for the test, so can you show that if the thermal runaway event appears, it's going to be contained within the battery. There's two ways, actually there's three ways, but the two first, it's either you have your battery pack, you overcharge it until minimum 2 cells go to thermal runaway, or you overheat it, you enter it back in the oven until at least 2 cells will move into thermal runaway. You can imagine that if it's the entire pack that's overcharged, or if it's the entire pack that's overheated, well, chances are it's more likely that more than 2 cells will go thermal runaway. The entire pack is overheated, or the entire pack is overcharged. So keep that in your mind. We're going to come back later on that. And there's another method here, the third one, that's on the VO211A on the appendix C. This one is slightly different. You just trigger 2 cells in thermal runaway at different locations, and you see what's going to happen with that. So it's not the entire pack that you're charging. You have your pack fully charged, but now we're going to trigger 2 cells at different locations, and that's another accepted method from the VO211. So this new wave of our light aircraft needs a new regulation framework. The European were the first one to launch the dance, if you want, with a bunch of special conditions. They had requests, so the industry was pushing for that type of aircraft. So they did release in 2020, 2021, 2022, 2023 a bunch of conditions to get closer to define those requirements. Here the propulsion unit, and now in that one here, they start to include the battery in those requirements. And at the end of 2023, with the evolution of the VTOL or VTOL aircraft, now they lay out here actually what's the requirement, what they want the industry to show as the test. So it's the 311A. In that case, with a minimum of 20% cells going to thermal runaway. So it's not the entire pack, it's not 2 cells, they're going for 20%. Regardless of the method, you can use overheating, overcharging, you can use appendix C, but your test is valid if you reach that 20%. And they're asking for a cell to be triggered thermal runaway, and they want to show that there will be no propagation to other cells. So that's for the VTOL that they did in 2023. By the end of 2023, so almost 2024, they inform us of a prediction or a forecast what they want to do with other type of aircraft. So they read here that 20%, but here for CS23 level 1 aircraft, with a small aircraft, they claim that, well, you can use that one, the same as the VTOL, or you could show no propagation if you go with 2 cells. So you trigger 2 cells, and if you're able to show that there will be no propagation, well, you're good. That's not adopted. It was part of a roadmap. It's part of a seminar, so it's still in the air. But that's what they were. That's what they showed us back in the end of 2023. Looking at the American side, we're still on that good old AC-184. That's from 2015. That's still look at the 311, not even the A, but just the pure 311. But it's been revised. Actually, it's actually in draft. It's been in draft since 2018, but never released yet. So it's still somewhere. We can consult the draft, we can see the draft, but not adopted at the moment. That one, the revision A, does include propulsion battery, so we can see that. It does reflect the new version of the 311A. Actually, it does not recognize the appendix C, so it says that it's not an acceptable alternative. So they're moving away from the 2 cells. So we can see kind of a split with the European. It was, when you look at their guidance material, it was there, the A, although in draft, but as to 2023, they removed it from the website as a draft, and now they say that it's not it's not to be used. It was drafted still. Now they are to make sure that you won't use that. And still on the FAA side, well, they rely on the standards, the new standards, the ASTM standards, but they're not yet universally accepted for aeronautical aircraft. And there's some SAE standards that are fairly new, like the 7131 that talks about their terminal runway as well. So give us some guidance and some ways to do that. We have also the CMT, so the Aerospace TCCA, which released a normalization paper about terminal runaway philosophy in 2024, so last year, so to give us some guidance, so everyone sat together and tried to sort things out, because everything was everywhere in the cloud. So it gives us some definitions of the protections layers, and they show with no shame that there's some difference between the authorities, where the European are looking for something that more based on the industry consultation, as the American more on the use of the known standard. So they agree to disagree on that. It's a philosophical view, that's it, on this. Although they disagree on some items here, they do define some requirements for the containment of the terminal runway at the battery or at the module level. They want to see a single test propagation. They want to see what we call the N+1 test, so with more cells, and to see what's the threshold before there will be an actual propagation. And the multiple cells, so a bit linked to the DO311A, and you render enough cells that you're going to reach a 20%, and you ensure that your pack can contain that. And when we say contain the terminal runaway, it's either it's contained within the pack and that's it. It's what we call a level A pack, and you have a level B pack, which is there's an exhaust and you can exhaust everything of the aircraft. And there's also a level C, which not contained and not sealed, and we don't lose that. There was a response from the industry to that white paper from the Gamma EPIC committee, which is to advocate more for to go beyond the pre-prescripted pure containment, but go more with the performance space. The fear is that if you go just pure containment, let's say the 20% or more, you're going to end up with a battery pack that's so heavy that it's going to kill the project. It's going to kill the actual energy that's on the battery, so it will not work. You won't be able to fly. So they're going toward more that let's look at the non-propagation rather than this pure 20%. So let's show that if you have one cell, two cells, or a number of cells, that they will remain contained by themselves, and they will not go further, so that not the entire pack is going to go to terminal runaway. So that's the philosophy that they're looking for. Some consideration on that. Of course, the applicant must bring the data to show that it's going to be contained, and to define that number. If not 20%, what it is, that famous N+1. So what it is. So you need to show that and see, well, based on your design and based on your quality of your cells, the quality process, to bring to a number that will be agreed by everyone. So that's what it is. So currently there's two main design philosophy. It's either prevention layer, so that's the one where we'll make sure there's some barriers inside of your battery module, and you have a good quality control system that your cell by themselves, they're good quality, and they will not trigger themselves into terminal runaway as it happens 10 years ago in some computers or some cell phone. And the other philosophy here is pure containment, to make sure that whatever happens here, well, it's going to be contained. So how does that relate to our current project? So first, the project itself. So it's we have 4 battery packs, 86 kilowatt hours, 800 volt nominals, 2 channel string, 2 packs in the wings, 1 forward of the firewall, and 1 at the back in the cabin, so we're replacing the 2 seats down the back, and a battery pack is going to replace that. Each battery pack is going to contain 10 modules, and those modules are made of 120 cells with some thermal runaway passive protection, so some barriers to prevent propagation. It's a category B venting, so there's ports to exhaust of aircraft if there's a thermal runaway, and there's a battery or module management system to monitor the cells and cell voltage and temperature. Our vendor for the battery here at this point proposed a qualification test for containment. It's based mainly on the Appendix C of the 30311A at the module level with charged cells, and to go with your worst case, your battery are warm, and you're gonna go well as the Appendix C, so you're going to trigger 2 cells at different locations and show no propagation from that. That's the goal, and passive, using only passive resistance. So the battery management system will be disconnected with just the passive barrier that's going to be active at that point. As Appendix C, there will be repetition of that in different locations on the battery pack to show all the possible cases. And from that, get the data at the module level. So what's the temperature exterior of the model? What's the temperature at the exhaust, to make sure that the actual pack can sustain that, to make sure that there is no propagation between the packs, and make sure that at the output, at the exhaust, there will be no harm, and the exhaust system can sustain this pressure that will go, sudden pressure that will go there. And next step, where we are in this project, is to review the final battery design. It's been, of course, as you can imagine, a lot of iteration and a lot of evolution. So now we are looking for the final design and justification on why and how we're going to use that number, the N+1, the 2 cells. We have to look into this. And so the takeaway we have, well, we're at a new pivotal phase for this type of energy in aircraft. It's a highly dynamic and evolving environment, as you can see from the regulatory point of view. And we're on we don't have. We're working on walking on the thin layers of standards that are being adopted or not, and being defined as we go on this project. Of course, there's multiple projects out there. There won't be one straight forward solution path. It might be none. We'll see. And for now, the compliance, it's on the case by case, of course, basis. And obviously there's more than just thermal runaway. We did the thermal runaway, and we'll see later this morning that it's going to be way more than that. Now I'll give the floor to Erica. Yes, I will do.
We started pretty late this morning, so I might end up running into our break unless you guys all decide to exit in the middle, which is your choice. I'm going to do a little departure here. We're talking a bit more about the operational maintenance considerations through the experience of flying our experimental aircraft. There we go. Yeah. Just a little bit of context. DHC-2 Beaver, 450 horsepower, 5,600 pound gross weight aircraft. We installed the Magni 500 kilowatt-hour engine in it. It's been derated to 338 kilowatts, so it matches the same power of the original aircraft. The purpose of that was so that we didn't change anything we didn't have to change. Yes, a lot of people complain, pilots especially, that the aircraft is underpowered, but we didn't want to change it if we didn't have to change it, keeping the change as minimal as possible. We have a 156 kilowatt-hour battery pack. We have been through 2 iterations of the battery pack, and that's sort of my focus today, our experiences with the 2 different types of battery modules that we had and the 2 different systems that we ran. We've been flying it to really simulate things like LPC behavior, cooling behaviors, and operational considerations. I'm not going to go through all of this, but this is trying to get us all on the same page as to definitions, right? You have your battery cells, you have your battery modules, we have what we call stacks, and then we have what we call strings. The terminology has not been fully agreed upon yet, even within the industry. This is the terminology that we are using, so we're all on the same page when I describe our particular system. This is the first iteration of our battery pack. It was 3 strings. So think of it as 3 separate fuel tanks. They all fed into one single lane that fed into the engine. So that if you ever had a fuel tank or a battery string go offline, you still had the others feeding the engine. You didn't have a loss of power at the engine stage. Those battery modules, the form factor, as you can see, was not ideal. We have a lot of empty space under the floor, so a lot of it ended up just being stuck in the middle of the aircraft at the CFG, and that was because it was our experimental aircraft, not intended for cert. This was intended for exploration to try and understand the technology that we were dealing with and determine if it was even commercially viable or not. At this time, those battery modules, each one, weighed 85 pounds. And they came in 10% heavier than they were advertised by the manufacturer. So when the first one arrived and we weighed it and discovered this, we went from actually expecting to install 9 batteries per string, so 27 modules. We were only able to install 24. Our first flight was anticipated at only being able to fly for 8 minutes, given the calculations that we had at the time. Not commercially viable, but really fun as an engineer. 1.5, so we took those modules out and we installed a completely new system. These modules are quite a bit lighter, but still heavy. We did get a little bit energy density in these particular ones. And this time we went to a 4-string system, and each string fed an inverter. So basically, you consider it multi-engine kind of architecture. There's a battery link feeding an engine, and there are 4 of them, right? But this means that if you lose a battery string, then you also lose 25% of your power capability at the aircraft level. For us, this absolutely does not matter. This engine is incredibly overpowered for our particular application. Like the Magni 650, which is the target certification engine for this, is capable of like 900 horse. We only need 450. So the loss of that, actually, we can have each of the inverters overpowered a little bit so that if you had a loss of one, it'd nice and probably get back to 100% power. So it was a very different setup. In this, it was interesting that the system safety analysis was 6 of one, half a dozen of another. I thought that was interesting from our guy about whether or not having them all bust together or not bust together didn't make a material difference at the aircraft level from a system safety analysis. So this module, this was kind of interesting, going back to some of the stuff Francois was talking about in terms of strategies around the modules themselves. This was considered a propagation mitigation strategy. So if a cell went into thermal runaway in this configuration, then the aluminum block was to wick away the heat to prevent propagation to another adjacent cell. The impact at the aircraft level, so I want to talk about this a little bit from a design engineering perspective, it really changes, and I'll show that in a couple of slides, what you have to do at the aircraft integration level. The exchange, of course, is weight. This thing was bloody heavy. And it took all we could do for the engineers to actually, the AMEs, to get them in and out of the aircraft, and those poor guys had to do it about 15 times, so. These are the new modules, which is a containment strategy. So basically, the module itself is a fire containment zone. I know we're looking for definitions here too for what we consider for containment for batteries. One of the thoughts is that could be the containment zone. You saw that in the aircraft. The other, you don't need any additional fire shielding. At that point, you would still have bulkheads to block off, but you don't need fire shielding from these because these ones, that is effectively the fire shield. So this one, though, it goes into thermal runaway and it just allows it to cascade throughout the module. There's no propagation mitigation. That's a little bit more just about how the vent system actually works. Just get this. This is the one I really wanted to highlight. So for us, the first battery system we installed some like skeet tubing on it. It weighed like 5 pounds for the entire venting system once we manifolded it together. It was incredibly light. There wasn't much for us to manage. In terms of what they call the ejecta coming out of the modules, there was very little coming out of those modules because you'd have a cell or two go into thermal runaway, have some gas come out. It's ugly gas, but it was just gas. The second one, because it burns everything inside, you have a significant amount of ejecta coming out, right? So for that one, we were given numbers in the range of 1100 degrees Celsius for 8 minutes. That is a lot to manage at the aircraft level. And so our system ended up weighing, it was pretty close to 70 pounds. That is a huge penalty to pay for that version. But on the other hand, the other one, you had a very heavy module, even though you had a lighter installation. So if you're looking at, when you're doing your design selection and product selection, if you're working in this arena, these are just considerations to look at. What is the mitigation strategy of the OEM who is producing your battery product? In terms of lessons learned, there's a lot. I could probably spend another hour up here talking about all the things that we experienced flying these things. A lot of it had to do with the non-linear charge rate. This was something that if you are trying to sell this to a customer and they are an airline or an operator, how they dispatch the aircraft becomes completely different. So a company like Hardware, where we're doing charter flights, we're doing tours, we're doing scheduled flights, there are some that are really easy to manage, right? For a tour flight, you're doing 15, 20 minutes. You don't charge all the way up. You're probably just bouncing between 40 and 80%. That is the linear portion of the lithium-ion charging, and that is easy to manage. And you can predict how long it'll take to charge given your chargers that you have available. But if you suddenly now turn around and want to dispatch that aircraft for a longer charter or a long sched, you need to now charge it probably up to the 100%. It's not linear. So suddenly what was maybe a half hour, 45-minute turnaround time, which is what we were targeting, could be an hour and a half. Your dispatch personnel are going to struggle with that. Air traffic control is going to struggle with some of these things. We were flying the other day. I was in one of our aircraft flying across, and because of ATC controller shortages in Vancouver, we kept getting diverted around the control zone. And you're not. I mean, it's built into the reserve, but it's something that we really have to be paying attention to. There are some dispatching things that are different about these vehicles right now. Cooling. Cooling was a big one. Temperature control, temperature management. It wasn't just that it got hot or that it got cold. It was that we had temperature differentials. It was an extreme temperature differential, partially because we were operating on water. One of the things we noticed when we were trying to charge at the dock, the ocean is an amazing heat sink, and it draws the heat out of the bottom. So we had modules in the bottom of the aircraft. We didn't insulate it because we didn't want to keep the heat in. In hindsight, that probably would have been beneficial because the ocean was sucking the heat out of the bottom so rapidly, we would see an 8 degrees Celsius differential between the cells in the bottom of the module and the cells in the top of the module in the module that was in the belly of the aircraft alone. Then between that and the modules that were inside the aircraft, we were getting greater than a 15 degrees Celsius spread, which usually kicks off the charger, and the charger refused to charge at that point. So there is some significant, it's not just about the overall temperature, which I still think, I know the system we are both looking at, they are dedicated to air cooling. I am a firm believer in ground conditioning and liquid cooling. I am not convinced at all that air cooling is going to be enough. If I'm flying from Vancouver in the summer and it's 30 degrees out and I want to fly this thing 12 times a day for tours, I do not believe I can turn that around with an air-cooled system. Yes, I know. But I'm going over. If everybody chooses to leave, that's your choice. We are technically at time, but the minister ran over, so I'm going to keep taking my time. He set the precedent, really. The cycle thing, storage and cell balancing. So this was really interesting. I know there's WISA, the Waterloo Institute for Sustainable Aviation, has a couple of pipistrels, and one of the pipistrels, they stored it for a brief period of time, and they stored it at closer to 100% state of charge. A couple months later, the state of health was significantly degraded on those batteries. These are things that we're going to have to consider. There's a lot of educating. We're not just making product. We're not just certifying product here. We have to make product that the operator knows how to use. We had a significant issue with cell balancing in our first system. It's one of the reasons we had to change from our first system to the second system. Apparently, the OEM thought it was a good idea to install software that would gauge all the cell balancers when the software is connected to the aircraft. So we were balancing the aircraft quite frequently because we had a parasitic draw in one of the strings. And this system then was setting off every balancer in every cell in every string, whether it needed it or not. And we ended up working the battery system so hard that we had to replace it after only 70 flights. These are things the operators are going to need to understand, and we need to build a product that's more robust so the operator doesn't have to worry about these particular things. How are they going to manage? Are they storing it in a humid condition? Are they storing it outside? These are all things that right now are problematic. We had an issue where we put the aircraft outside for a while. Yes, we can't fly in rain, but we thought it could sit outside in the rain briefly. No, it cannot sit outside in the rain briefly. Water ran down one of the cable leads, got in through the braiding, got into the connector, and now when they went to turn the aircraft on, they had a loss of isolation fault. Bit scary when you're dealing with 800 volts, when you suddenly are told that there's a loss of isolation. The AMEs were not particularly enthusiastic that day. But we did figure out, we put the big white suit on and we figured out where the problem actually was. One thing I also want to do from a maintenance consideration point of view, things such as the line replaceable units, one of the things we found, we had a box, a very expensive box, it was a $10,000 box. It's a magic box, I don't really know what's inside the boxes, but I do know one of the things that's inside the box is, aside from the high voltage components, there are low voltage protection components in there. Things as simple as fuses. And they haven't separated it out. They basically have given you a box, a really expensive box, and there are things in there you should be, as a mechanic, able to replace, and we cannot. We had to take the box out of the aircraft because a little bit of smoke came out, send it back to them, so they could replace the fuse inside the box. We need to work with the suppliers to understand what they keep in their sandbox, but what is actually able to be pushed into the sandbox of the mechanics. Right now, they don't actually know where that division is. Charging infrastructure was also a really interesting one to me. I think that if you look at the future right now, we're going to be adopting this on the smaller aircraft first, the pilot trainer type aircraft. These are aircraft that are going to be operating at community airports. They do not have 480 volt, 100, 200 amp service available. So you have all these companies out there like Beta and Electro or whatever they're called. They're creating lovely charging boxes that are really nice, high-speed charging boxes. They're not going to work at any of these community airports. They don't have the infrastructure, the power infrastructure. When we changed from a 530 volt system from our first battery system to the 800 volt system of the second battery system, there were no chargers available that could run on 220 volt single phase so that we could charge to full. We had a 7 kilowatt charger, but it was only capable of going to 750 volts. It couldn't get to the 800 volts. We are highly dependent on the automotive market. And the automotive market was all around 550 volts, give or take, for all the battery packs. So that's what all the chargers were. There's some change right now. You see Polestar and some of the others creating some higher voltage systems. But if we want to adopt these aircraft, the initial adoption at community airports, we also need the charging infrastructure to go with it. And I'm going to leave it at that. I don't think we have any time for questions.